All right, I do want to welcome you back to Unit 10. This is thermochemistry, and I thought a good way to end this unit would be with a just general discussion of something called thermodynamics. Thermodynamics, what do we mean by that? Well, in chemical terms, what we mean by thermodynamics is whether a reaction is spontaneous or not. So we're going to be looking closely at something called the Gibbs free energy, or the delta G. Now, what do we mean by Gibbs free energy? It's the free energy change, and it's represented by this delta G symbol that we've talked about. Delta G is the maximum amount of energy available from any chemical reaction. So that's what we mean by delta G. So what information does it give us? Well, it tells us whether the reaction is spontaneous or non-spontaneous. What do we mean by spontaneous? What do we mean by non-spontaneous? Well, we mean the propensity for a reaction to move in the forward direction. So let me give you some examples. Rust, for example. Iron is going to inevitably oxidize, right? Fe is going to become rust. Iron is going to become rust inevitably. It is a spontaneous process. That doesn't necessarily mean it's going to happen fast, and we know that it doesn't happen fast, but it's going to happen inevitably. And that's in essence what we mean by spontaneous. The reaction is going to happen inevitably, right? So, two forces then drive chemical reactions. The first is enthalpy, or delta H. We've already talked about delta H extensively in our discussions of Hess's law. And again, delta H represents the change in the internal potential energy of the atom. So in the process of breaking apart molecules and reforming them, a certain amount of energy is going to be either required or released depending on whether the reaction is exothermic or endothermic, right? So that's the first driving force. The second driving force is an increase in the entropy of the system. We're going to be talking a lot more later on in this particular screencast about entropy. But entropy also plays a role in whether a reaction is thermodynamically favorable or not. Now, let's put this all together into a chemical, or into an equation. And here it is, a very important equation that relates delta G, delta H, and delta S. And here it is. Delta G, that's the spontaneity or Gibbs free energy quantity, is equal to delta H, which is the change in enthalpy, minus the temperature, it has to be in degrees Kelvin, times the change in entropy, or the delta S. So this equation right here is going to relate those three variables to tell us whether a reaction is spontaneous or not. So let's take a look at an example. The question is the combustion of propane a spontaneous process at 298 Kelvin? And they tell us that the delta S is 100.4 joules per degree Kelvin. Now, we've already looked previously at this particular compound. We looked at propane. We were talking about Hess's law. But what we want to do now is determine whether this process is spontaneous or not. Will it eventually, inevitably occur? That's what we really want to know. So here's how we would arrive at the solution. From Hess's law, we looked at the delta H and found it to be negative 2044 kilojoules. So that was the number that was arrived at. It was a negative number. That meant that the process was highly exothermic, right? That it gave off a lot of heat. Now we want to know, is this process spontaneous or not? Well, we're going to use the formula delta G is equal to delta H minus T delta S. We'll just plug in. So delta H, you recall, was a negative 2044 kilojoules minus the temperature. I'm told that the temperature is 298. So that goes right there. And I'm also told that the delta S, or the entropy change, is 100.4, right? 100.4. And I'll put that number just like that. So now I'll do the math. One thing I've got to be careful with though is this. Notice here I've got delta H in kilojoules, but over here T delta S, when I multiply Kelvin times joules per degree Kelvin, the kelvins are going to go away, but I'm left with joules. Can't do kilojoules minus joules, so I have to then divide by 1,000 to go from joules to kilojoules. So I'll say 298 times 100.4, then divide by 1,000 to get to 29.9 kilojoules. So then I'll just do the math. Minus 2,044 kilojoules minus 29.9 kilojoules. This is my final answer. It's a minus 2,074 kilojoules. Now, what does that mean? Well, obviously 2,074 is a big number, but it's also negative. What does that mean? It means that since the delta G is a big negative number, that this process is extremely spontaneous. This process is extremely spontaneous. And anyone who's ever lit a propane barbecue grill could have told you that, okay? So that's that. So we've done an example then, helping us to understand how to calculate delta G. Let's do another one. So this is example 2 now. The question is, what is the value of delta G at 300 K for a reaction in which delta H, I'm told, is a negative 150 kilojoules per mole, right? So that is then an exothermic process, and the delta S, I'm told, is a plus 200 kilojoules per mole per degree Kelvin. So the formula that I'm going to use is this one right here. I want to relate delta G, delta H, and delta S through temperature, right? So here we go. Delta G then is equal to minus 150, that was the delta H, minus the temperature, I'm told that is 300 K, so I'll plug that one in there, times the delta S, which is 2.0 kilojoules per mole per degree Kelvin. I don't have to worry about the conversion here because this is already kilojoules per mole per degree Kelvin, and so what I get is minus 750 kilojoules per mole. Again, a negative delta G. What does that tell me? It tells me that this is a spontaneous process, right? Because it's negative, it is a spontaneous process. All right, just a couple of ending notes. The first is temperature. Remember that temperature is a measure of the average kinetic energy of the particles, right? So the greater the kinetic energy, the higher the temperature. The greater the kinetic energy, the higher the temperature. And the temperature is measured in degrees Celsius or degrees Kelvin. How do you convert? Well, you can say Celsius or degrees Celsius plus 273.15 will give you degrees Kelvin just like that. So if you want to go from Celsius to Kelvin, just add 273. So that's that. And then just a couple of final notes regarding delta S, and that is this. Remember that entropy is a measure of the disorder of a system, and that the second law of thermodynamics says that everything in the universe is going towards greater entropy. It's going towards greater disorder. If you can take a photograph, and scientists can do this, they can take a photograph of what the universe looked like millions and millions of years ago, and they can see that the universe looked more ordered millions and millions of years ago than it does today. How do you explain that? Well, the universe, we know, is becoming more disorderly. Everything is becoming disorderly. All right? Now, that's not to say that we cannot, as human beings, produce greater order, at least in the short term, right? So, for example, we can build pyramids in Egypt, right? But eventually those pyramids are going to fall down. We can build skyscrapers, but they're going to fall as well. Entropy is ultimately going to win. Ultimately, everything in the universe is going towards greater entropy, greater disorder, all right? All right, so again, entropy means disorder. If your bedroom at home is nice and neat, that's great. The entropy is small. But if it looks like a tornado just went through it, the entropy is large. There's a lot of disorder in that room. So again, delta S then is the change in entropy. One last example with regard to entropy. Let's take a deck of cards, and let's just say that those cards are nicely, neatly stacked. In fact, they are arranged, ace, king, queen, jack, and so forth, so that the entropy of the system is low. There's not very much disorder in the system. But then if I just go outside and throw those cards, that deck of cards that was nicely stacked, up into the wind, and the wind distributes the cards all over the ground, then I have increased the entropy, right? The disorder then is going to be high when I throw those cards up into the air and let them fall wherever they're going to fall, right? So the entropy is going to be high. All right, now, if you move towards greater disorder, delta S is positive, and nature again favors this. If you move toward greater order, delta S is negative. So gases have a higher entropy than solids because molecules which make up gases are randomly moving around and banging into each other. So generally speaking, when you make gases, when they are formed in chemical reactions, the entropy increases. When you make gases, the entropy increases. So since delta G is equal to delta H minus T delta S, spontaneous reactions or spontaneity is favored by a larger delta S. So let's look at the equation again. If this number, the delta S, is big, all right, if it's a big positive number, right, that means spontaneity is increasing. That would make this number a big, it would make this number, let me erase that and redo that, the delta G, a big negative number, which would mean it is highly spontaneous. So if delta S is very large, that means I have a large entropy. If I have delta G that's very negative, that means I have a highly spontaneous reaction. So one more time. Large spontaneity, large delta S favors great spontaneity, a negative delta G. Does that make sense? All right, and let's finish this up with a final discussion about catalysts. And you probably already know this, but I just want to make sure that we don't leave any stone unturned. So here we go. Catalysts speed up chemical reactions by lowering the energy of activation. You know that already. If I look at this potential energy diagram, remember that the reactants are on this side, the products are over here, and then in going from reactants to products, I have to go through this higher energy level, and we call this the activated complex, right? Now, what you see in the blue is the normal reaction. From here to here, from the reactants to the activated complex, we call that the energy of activation, just like that, the energy of activation. Catalysts lower the energy of activation. They provide an alternate pathway. So for what you're seeing in red here is the altered pathway with the lower energy of activation. So you reach the energy of activation with a lesser amount of energy. It's required, less energy is required to get to the activated complex, so the reaction speeds up, right? The reaction speeds up. Now, again, this is what we see here is an exothermic process because products are lower in energy than reactants, right? And the activated complex is up above. Delta H is going to be from reactants to products, and the energy of activation is going to be from reactants to the activated complex. Folks, that's going to do it for this one, and that'll do it for this unit, and I'll see you on the next one. Thanks. Bye-bye.